Hi everyone. In the first video we talked in general about unsupervised learning and the k-means clustering algorithm. I left you with this exercise that is on the screen right now. We're going to take that up in the live class. So what I want to do in this video is just show you SKLearn, the SKLearn implementation of k-means. And then we're going to walk through the assignment as well, which is a little bit different this year than what we've done in previous years. I'm pretty happy with it. I'm kind of excited about it. So let's start by just going into the code here. Let me just run this code. I'm just going to start by getting the data set. So this is the same data set that I was using before. Just to remind you, I could do centroids and assignments equals k-means data 3 show, oh no, we don't want to show the plots, data 4. So I just did a clustering using my own algorithm with 4 centroids, and these are the centroids that it found, and the assignments we can look at those later. But what I want to do now is do it with the official SKLearn implementation. So there's a little tutorial right here in the comments of the code that I gave you. So we're going to import it. Fortunately, theirs is named a little differently. It's a capital K, so I can have both of the implementations going at once. And then we just create a k-means object. Just call it km. K-means, and there's a bunch of parameters as usual, and we'll look at some of them, but the basic one is n clusters. So that creates a k-means object that will use 4 centroids, and then we can just go km equals km.fit data, and that will that does the k-means algorithm. It actually does it by default, I believe, 10 times, and takes the best clustering based on the minimum inertia or sum squared error. So it looks for the one with the lowest error. You can configure all that. Once it's finished, you can ask it what its cluster centers are, and they're here, and you can compare them to mine, or the ones, so there you go, 2.62, 3.1, 2.8, negative 2.7, close, negative 3.3, negative 2.9, yep, and negative 2.4, 2.7. Negative 2.4, 2.7. Yeah. I may have mismatched those. Oh yeah, this one matches this one here. Sorry. Yeah, they're actually a pretty good match. They're a pretty good match. Okay, so that should be no surprise. It should come out with more or less the same cluster centers for the same data. If you take a look at KM labels, these are the assignments. So this should match the assignments that I came up with here. So let's look at the first few. Oh, but I think what's happened here is that centroid 2 and centroid 0 are flipped in theirs. So I went 0, 3, 1, 2. Theirs is going to be 2, 3, 1, 0. Or mine's going to be 2, 3, 1, 0. Sure enough, there it is. And the next one's going to be 2, 3, 1, 0 again. Interesting. Oh, that must say something about the way that I generated the points. It's the same sequence each time. Yeah, that says something about how the points were generated. Anyways, it's the same clustering, the same assignments that it came up with, but it's using the SKLearn implementation. SKLearn also gives you the sum squared error, which it calls inertia at 149. Okay, and it also has a predict method. We didn't do test and training data. I mean, we could do that, but we'll just give it the original set of data, and it will cluster it. It will compute the distance to the clusters. So if you want to know, you can do some little tricks here. You've got your KM cluster centers right there. So if you want to create an array of the cluster centers from this, if you wanted to do that, little hint, this might be useful for your assignment, you can go km.predict data, and then you can index into km.cluster_centers like this using the predictions, right? So the predictions are basically an index into here. So what this is going to do is it's going to create an array that's the same length as this, and the first item is going to be cluster center 0, next one's going to be cluster center 3, and so on. So there you go. So this represents for each point in the data this is the center that it was closest to. So that's the center for point 1, that's the center for point 2. I was calling them centroids, but they're calling them cluster centers here. Okay, that's basically it. That's basically all that you need to know. Let's take a look at, just real quick, SKLearn. So there's a couple of links here. One goes to the, see if these links still work, I didn't check them. A little discussion of clustering and different methods that they have here for clustering. You can see there's a bunch of them here. But we'll also take a look at the K-means API. That's the main thing. So these are the parameters that you can put when you create it. You can have, this is the one that you'll use. The default is 8 clusters for some reason, but this is the one that we're going to change. So I would have called it K, frankly, but they call it N clusters, whatever. It's just like for K nearest neighbor. And let's just take a look in the, what did I want to point you to? So yeah, initializing the centroids. You can change the way that they're initialized. So the way I did it was I chose K points at random from the data. But you can use the default in SKLearn, which is to choose smart initial centroids. So if we take a look, I think that's in it. Defaults to K-means ++. So this selects initial cluster centers, initial centroids in a smart way. You can look at the notes, but it's going to try and evenly space them, make sure they're not too close together. That's what it kind of boils down to. Or you can go totally random if you want. So choose. Yeah, you use actually this uses actual data points. So neither of these are quite what I did, but this takes if you've got K equals 4, it chooses 4 points from your data to use as the initial centroids. This is the number of times it's going to run the K-means algorithm. By default, it runs it 10 times. If you're finding things too slow, you could lower this parameter a little bit. But the lower it gets, the more of a risk there is that you'll end up with a non-optimal run. You can also specify the maximum number of iterations, and you can specify a tolerance. So it talks about convergence here based on tolerance. So one way to look at convergence is, do the clusters change from one iteration to another? Another is to just look at the amount of difference in the sum squared error, the inertia between the last run and the current run. And so that's you can set that tolerance parameter here for its stopping condition. But you probably won't want to mess with that stuff too much. Oh yeah, verbosity is kind of fun. So you can set verbose equal to 1. Wait, where is it? So verbose equal to 1, and there's a few other parameters you can play around with as well here if you want. You can also try and take advantage of parallelism if you have multiple cores. You can specify how many cores you want it to use. By default, I think it uses all of them. Doesn't actually say. Oh no, yeah. So you can decide how many cores you want to use for this thing. That's if you're doing real high performance stuff. So I wanted to do, let's do it again, km.fit data. Actually, let's start with, let's reinitialize here, and then we'll do fit data, and let's do, oh no, sorry. We have to do this when we do this, verbose, and then we do our fit. Boom, and you get a bunch of information here. So you get your initialization complete, iteration 1, 2, and 3. So it hit convergence at iteration 2 here. So it's doing 10 runs. And you can see that it doesn't take it long on most of these runs to find convergence, probably because of the way that it's chosen, the smart way that it's chosen the initial parameters, the initial centroids. Oh yeah, center shift 0.0 within tolerance. So yeah, it's actually the tolerance, sorry, is how much it's not the inertia that's changing, it's how much the centers have shifted. So in most cases it doesn't require very many iterations to come up with a solution. If we were to create it with, I think it's init equals random, we might see, yeah, because of the random initialization, because it's not choosing the centers in as smart of a way, it needs to go through more iterations in some cases. Look, here it got stuck in a bad one. Couldn't get better than 500 here as well. But in most of them, it manages to get it down to 149, 150. Okay, that's the k-means algorithm. Now, let's talk about what I want you to do with it. In previous years, we've gone back to the UCI machine learning repository, and I cooked up a kind of an artificial assignment based on that. But there's other things you can use clustering for. And one thing you can use clustering for is something called color quantization, which is kind of fun, I think. So it's a little different, and we're going to have to do some image processing. But the good news is that there's an image processing package called SKImage, scikit-image, which makes this very easy. And I'll show you some sample code. But let me explain to you the assignment first. So here's an image I took from the Trolls movie. Here it is, the original version, and here it is color quantized with k equals 10. So what I've done is I've gone through the image and I've chosen 10 colors and then mapped each individual pixel to the closest color. And I chose the 10 colors using k-means clustering. So if you think about it, what we've got here is a big two-dimensional array of pixels. Each pixel has 3 values, red, green, and blue. So if we take that, if we say this thing has, I think it's 500 by 800. So 500 times 800 is what? 400,000? So there's 400,000 pixels. If we can make a list of them, and each is RGB, so we've got 400,000 rows and 3 columns for the red, green, and blue values, ranging from 0 to 255. And then we cluster. In this case, I used k equals 10. And it clusters those colors around centers, around centroids. And each centroid is a color. So we cluster the colors that way. And then we go back into the original image and we replace each pixel with its closest cluster. So, and we get a result that looks kind of like this. Okay, so you reduce the number of, whatever k you give it, you can reduce the number of colors. Now, SKImage makes this really easy to load in an image. It gets you a two-dimensional array of pixels. All you have to do is, which is a three-dimensional array. All you have to do is turn that into a two-dimensional array, run the clustering on it, replace the pixels with the closest ones, and then turn it back into a two-dimensional array again. And fortunately, it's a lot easier than it sounds. And here's another use of quantization. So I took a cat image here from SKImage. This was a built-in one. They have, just like SKLearn has some built-in data sets, SKImage has some built-in images. I want you to use your own images, though. So this one's called Chelsea. It's a picture of a cat, maybe named Chelsea. And I used the quantization from the Trolls image and mapped each pixel in the cat image to one of the quantized colors from the Trolls image, and I get this kind of neat effect over here. So you can kind of use one image to quantize, and then use those quantized values in a different image to create kind of a neat, dare I say, artistic effect. I don't know if it's artistic or not, but it's kind of cool. So that's what I want you to do with this assignment. Okay, that's the overview. So what you're going to do is, like I said, you're going to quantize with the k-means algorithm. So you reduce each image to a list of pixels. So here's your example. If the image is 100 by 200 pixels, you'll have 100 times 200, which is 20,000 rows, and then 3 columns. So your data has 3 features, basically, red, green, and blue, the red, green, and blue values of the image. Then you can use the k-means to cluster the colors. And each of those clusters, each cluster center will be an RGB value of a color. And then you create a new image map by replacing each pixel with its closest centroid. And you can also use the predict method with an previously unseen image that you've turned into a list of RGBs, and you can use it to quantize a completely different image. So for the data, I just want you to choose any 2 images. Don't use the built-in samples, but you might want to make them smaller. So the original version of my Trolls image was 800,000 pixels. It was taking forever to do these experiments with quantization. So just go into Paint and reduce it to like a quarter of its size. That'll cut the number of pixels by 8 because everything's squared, and it should run much faster. You can always do that for a little while and then use a larger version of the image for your final image processing to make it look nicer. You're going to write the code yourself using SKLearn, Matplotlib, NumPy, and the SKImage library, which is new. Okay, let's take a look at skimagetest.py to see how this works. So you have this code. I gave this to you. When you run this code, what it does is produces a bunch of images. So I was just messing around here, trying some stuff. It makes it really easy to do stuff. So first of all, I pulled out this Chelsea image, and I tried to grayscale it. I used two different methods. In the first one, I took the red, green, and blue values of each pixel and averaged them. So let's say for this pixel, the average red, green, and blue of the red, green, and blue values was 100. Then I would replace this pixel with the color 100, 100, 100. So a grayscale color. Because if the R, G, and B are the same, then you get a grayscale. I wasn't super happy with that effect. So here I looked up how to do it better. I converted the image to an HSV representation. So wait a sec. Let me show you. This is a little off the beaten path of what you need to do, but this is fun stuff. So, I go to create an image here. I go to More Colors. So here's my RGB color model. As I move around here like this and say OK, why didn't that work? Custom? Oh, because I have to change this here. There you go. It's showing me the amount of red, green, and blue. These numbers go from 0 to 125. Sorry, 0 to 255. HSL or HSV, hue, saturation, value, or luminosity. The saturation is how much color there is in it. So if you take saturation down to 0, the hue is in this direction. That's just a number that indicates the sort of the color. And then luminosity is the brightness, or value is the brightness, which is over here. So brighter, less bright. And then saturation is how close to gray it is, how much of that hue is actually in the image. So what I did was I converted, when you load in an image in SKImage, it automatically comes in as RGB, but there's a simple conversion method that converts it to HSV, HSL, and then I just changed the saturation to 0 in all of them. And that got me a much smoother grayscale image here. And then here, I just messing around with this Trolls image. All I did was I just took all the red out of it. I changed all the red values to 0. Let me show you how this was done. So I'm importing NumPy, because this is based on NumPy. I imported data, which is how I could get, there's a bunch of stock images in the data. So data dot, there's a bunch here, checkerboard, clock. There's all kinds of images that you can play around with. Some of them are grayscale, which is represented differently. You want to work with color images for this. So make sure, and you're not going to use those images anyway. But I picked out Chelsea. This is how you display an image, just using matplotlib, using pyplot. Create a figure. This is just the title of it. And then there's an IMShow method, and you turn off the axes so that you don't end up with axes labels down here and points plotted. It just shows the image like that. So pretty simple. Reading an image from a file, super easy. I had to import IO here, but io.imread, and just as long as that's in the same folder, it'll load it, and then I print that. I plot that image. Then what you get is, so let me show you here. Oops. So let's do this over here. So Trolls is a three-dimensional array. So see that it's at root, each pixel is an array of 3 colors. But each row, so if I go array 0, there's Trolls 0. There's the first row. So the first row is an array of pixel values. So it's a 2-dimensional array. So the shape of Trolls, if you use the shape method here, the shape field, is 800 rows, 1,000 columns, and then 3 colors in each column. Okay. So what you can do is, what I've done here is, I just said, take the Trolls array, all the rows and all the columns, but just the red value. So the first value in the red arrays, and change it to 0. And that's how I took the red out of the image. And I got this image here with the red removed. If you want to max out the red, you could change that to 255, and then you end up with like that. It just gives a red wash. Every pixel has its red value maxed out. So that's pretty cool. So that just kind of shows you how easy it is to manipulate this stuff. You get this 3-dimensional array, which you can think of as a 2-dimensional array of pixels, where each pixel is an array of size 3. and then you can just mess around with it using tools in NumPy. Here's my first try at grayscale, which was inefficient and didn't work. So I just said, give me all the rows and columns. Take the mean axis equals 2. So axis 0 is the rows, 1 is the columns, 2 is the axis that's going to sum it along the red, green, and blue values. So I rounded that off, and then I went. I couldn't think of a better way to do this. Maybe there's a better way, but I went through the rows and the columns and created a new color of 3 values that were the same. But that didn't look very good. So instead I imported 2 extra things. There's all kinds of stuff in SKImage. It's really cool. 2 converters, one to convert to HSV and the other one to convert back. So I convert it to HSV, hue, saturation, value. The first, so you get a pixel with three values in it. The first is hue, the second is saturation, the third is value. So I just changed the saturation to 0, like that. I wonder what would happen if I changed it to 255. Didn't try that. Yeah. Okay, so that changes the saturation. Oh, it should be between 0 and 1. So when I fully saturate everything, oh, there we go, that's better. I end up with, for some reason, a very red image. Not always, though. The eyes are kind of popping out there. So it's just really fun to do stuff like that, to do all kinds of cool things. And then at the very end here, if you have an image that you like, after you've plotted it, you can save it to show to distribute. So after you've done your processing, IMSave saves the image, and it's smart enough to read whatever suffix you put here. If you don't put a suffix, it'll save it in TIFF format. If you do, it'll save it in PNG or JPEG or whatever you want. So pretty cool. And that's most of what you need to be able to do this. The only thing that's kind of missing is that trolls is this 3-dimensional array. What we want to do is reshape it into, it's, I guess, an 800,000 by 3 array. And you can do that like this. Trolls, so equals trolls dot reshape. It's a method that's built into NumPy. 800 times 1,000, rows and 3 columns. And it's actually smart enough to do it exactly how you would want it to be done. So now I have all the pixels from the trolls array, but in a 2-dimensional array now. So each pixel, it's basically an array of 800,000 pixels. And I can put it back the other way, like this. 800 rows, 1,000 columns, 3 values in each. And voila, it's gone back to the way that it was before. And just to prove it, let's do this here. We don't need this line. Just going to plot it like that. Boom. There it is. This was after the processing. Notice all the red values are 0. But yeah, so I took the troll's image, I flattened it out, and then I put it back into a rectangle and showed it here. So you flatten it out, you put it into your k-means algorithm, do some fancy processing, which only takes a few lines, then put it back to the way it should be, and you can plot it and save it, and it'll come out just fine. So yeah, so here I'm showing you how to do that with a different image, 100 by 200. You simply reshape it, and then do your thing, and then shape it back. Okay, so what I want you to do is there's 2 tasks. The first task is to look for a natural quantization of the image. So I want you to quantize it using k-means. Figure out how to do that first, and then I want you to try it for a variety of k values. I want you to show each quantized image with the original and report the inertia for each run. So we're kind of trying to look for a natural quantization, like a natural clustering of the colors. And we're going to try to do it by trying to identify an elbow. Okay, so here's a sample output. Not all the images are shown, but here's k equals 2, then there'll be 3, 4, 5, whatever, k equals 10, k equals 18. Here's the output of the run, showing all the k values I tried and the sum squared error, or the inertia for each one. And here's a graph of it. It would be cool if you have a picture that doesn't have a lot of colors in it, or has only a couple of real hues in it. You might actually find a nice clustering, which would be cool, and you might see an elbow in this graph. I would argue this one doesn't really have an elbow, So in that case, if you could maybe argue these are elbows, but it really doesn't look like it. It just looks like it's a choppy curve. If you find a real elbow, though, a real place where there's a sudden drop in the sum squared error, and then after that there's no further drops, you could use that as your quantization value. Otherwise, pick one that you like. So I liked k equals 10, so I pick that. And then you're supposed to say this is your output, you're supposed to say in the comments which k you chose for the second task and why you chose it. So maybe you found an elbow, maybe you didn't. And then use a second image and quantize it using the quantized colors that you found from the first image. So that just means rearranging this into a flat array, calling the predict method, and then replacing the colors with the centroid values to get kind of a neat recolored effect like this. Okay, so that's it. First task, do a bunch of runs of different quantizations. Second task, identify a good k value and use it to quantize a different image. Okay, so I hope you guys have fun with this one. I could show you mine. Here we go, quantize. This is what mine looks like when it runs. I'm not sure why I used a step value of 2 here. It takes a while to do the run as well, even on a small version of the Trolls image. You should probably step by 1, and don't feel like you have to stay at low values. Try high values too and see what it looks like. I mean, the higher the value, the less the image will change because you're quantizing it, less. So here's what I end up with. Yeah, k equals 10. There's Chelsea. There's my graph. And here's all my different quantizations of the image, all the way down to k equals 2, which is actually kind of cool as well. I don't know why k equals 8 was on top, but whatever. All right, so is it machine learning? Yeah, kind of. I mean, it's k-means clustering, which is definitely machine learning. We're just using it for a different kind of task. We're using it for something that really is more like an image processing task. But my defense is I think this is a fun task, and it'll get you to learn this SK image library too, which is cool for image processing of various kinds. Okay, let me close this. All right, so I think you should get started on that, and we can go over some of this stuff again in the live class next week. But in the meantime, good luck on this. Do try the paper and pencil exercise as well, and I will see you in the live class.